that was me. Was ist das?
And that was a picture of
It's recording.
Timone's crotch.
No, it's recording now.
Why?
It's recording.
Because I'm going to critique myself later. I have to do this in
Yeah.
front of a classroom full of people.
And we have to close the window.
With
because
4
it's
people or full of people?
Can I give you this?
Yes.
That sounds like a good one.
Imagine there's a storm.
Very good.
Storm maker. Obviously.
Ja, mir fehlt die Schraube. Das ist ein Ventilator, das ich so drehen kann. Mit Fernbedienung.
Okay.
Oh.
Okay, so if you have questions, you can stop.
Hey! We're still live?
Yeah.
So,
Oh, yeah.
I have a question.
Yes.
What is today's topic?
Today's topic is O3, the group SU2, their relation to each other, and Euler Angles.
I've never heard one of those.
What is O3? What is it? SU2? What is
Yeah.
I've heard Euler Angles, but I
Okay.
have no idea what
Yeah.
they are.
Okay, so let's start. So we're going to start here, O3 and SU2. They're groups. What's a group? A group is a collection of elements and that is closed under an operation. It has the associative property. This collection of elements has the identity, and it has the inverse to every other element that's in it. It's a group. Okay, so O3 is a group that all of the elements are orthogonal, and the group is made up of all 3x3 matrices, which are orthogonal. So orthogonal is the property R, which is in O3. Okay, so orthogonal, this O, means that the transpose is equal to the identity. That if you multiply the transpose of an element times itself, it's equal to the identity. And also if you switch this, so R times R transpose is equal to the identity. Linear algebra.
1, 1, 1. Matrix.
Okay. So now this group has some properties to it. If you take the determinant, it kind of come out linear algebra because the elements in this group are all matrices. And the matrices will act on vectors in R3. So
You're so funny. People taking pictures of you.
So R acts on a vector where that vector is in R3. The purpose of the elements of O3 are to rotate things. So you have some vector in R3, so in space, and you act a matrix on it in order to rotate it a little bit. Okay, so a property of this group is that if you take the determinant of any of its elements, you get plus or minus 1. Now, you can take this property and split it up. So you can take all of the elements which have the determinant of plus 1, and all of the determinants would have minus 1. And all of the ones with plus 1 we call O plus 3, and all of the ones with O, the determinant minus 1, you call it O minus 3. Now, the identity has a determinant equal to 1, and so this group does not have the identity in it. And that means that it does not have a Lie algebra associated with it. O3 does have the identity, and it does have a Lie algebra associated with it. And that'll become more interesting later when we talk about how Lie algebra makes sense in this context. So this property, so this determinant equal to 1 plus 1, is called special. So we now call O3 plus SO3. And this is the group that we'll be dealing with from now on, SO3. SO3 is also a manifold, and it's a manifold in particular of which looks like a sphere with radius pi. And it's because the parameters which O3 depends on are defined on the closed interval negative pi to pi. So you could consider them x, y, and z, but because we're dealing with rotations, we call them theta 1, theta 2, and theta 3. And we have 3 of these because SON depends on n times n minus 1 over 2 parameters. Now, if we think about what a rotation is, if you take something and you rotate it by pi, and if you take that same object and you rotate it by negative pi, you end up with the same rotation. You get this is equivalent to that. So how that shows here is if you take, so antipodal points are the same point. So pi is equal to negative pi. So let's consider a path where we begin at the origin and go out to some point pi. We have that antipodal points are identified as the same point, so then we can magically come over here, and now we're at negative pi. And then we go back to the origin. And this heuristically can't be shrunken down to a point. If it were a closed path, for example, it could be shrunken down to a point. You could bring all these points into one point. But this structure cannot be shrunken down to a point. That means that the group structure is not simply connected. And this helps us in quantum mechanics. So in quantum mechanics, the physics is the same up to a phase factor. So you could multiply e to the 15 times any of your physics, and your physics is still the same. And that phase factor makes doing computations in quantum mechanics difficult, because you have a pesky phase factor to deal with. And so you have to work with what we call the projective representation of the group. And that's a really difficult method. But because it's not simply connected, it has a universal covering group. And the universal covering group is the smallest group, which is simply connected, that contains the original group, in this case, SO3. The universal covering of SO3 is SU2. So we do physics with SU2 instead. SU2, so we have S. We know what S is. It's special, and we define special being the determinant is equal to +1. And U means unitary. And for the O3, we have R transpose R is equal to the identity. Unitary now, instead of just transpose, it's transpose conjugate. So what a transpose is you have A, B, C, D. Let's call that R. So then R transpose would look like everything flips. So A, C, B, D. So that's what the transpose conjugate is if there is an imaginary number here, the imaginary number also becomes negative. So that's what the unitary SU2 stands for. SU2 depends on n squared minus 1 parameters. And it's SU2, so it's made up of 2 by 2 matrices. And like here, we had R acting on some vector, where the vector is in R3. Well, now we have R acting on some vector, but now the vector is in the complex plane, C2. So it has 2 parameters, and SU2 depends on these 2 parameters, what we call continuously, so it doesn't jump around. For example, you could think of it not having the identity being not continuous, because you can't get from the identity to any point in O minus 3, because O minus 3 does not contain the identity, so that's not continuous. An idea of what continuous is. So SU2 depends continuously on its parameters, so there's no holes in it, you might say. And because of this, it's a Lie group. Also, quantum mechanics. So SU2 depends on 3 parameters. 2 squared is 4 minus 1, so it depends on 3 parameters. And this is interesting because your 3 parameters are W plus, W minus, and Z, which are the gauge bosons for the weak force, because SU2 is the symmetry group for the weak force. And there are also SO3. Just a second on that.
Geht aus.
Weißt du, vielleicht macht das ja keinen Sinn. Vielleicht sind das nur
Du
Buchstaben.
verstehst es also auch nicht.
Doch, also ich kenne das mal mit Matrizenrechnung und Einheitsmatrix und sowas.
Ich verstehe keine Worte.
Ja, das ist Standardmathe.
Okay, sehr gut.
So ein bisschen, aber ich verstehe auch nichts davon. Wahrscheinlich, vielleicht ist es auch echt viel schwerer. Weil sie kann nicht alles aus dem Kopf. Oder
Ich glaube, sie hat sich darauf vorbereitet.
Ich weiß zum Beispiel bei den Amis, dass die im Economics so haben diese Sachen, die so leicht sind. Die sagen, wenn die von der Schule aus bringen, sie erstmal die Hälfte um, weil die in echter Welt so schwer ist und die in der Uni halt nichts lernen. Aber das ist ja schon ziemlich krass, so wie das wird.
Okay, I can't find my facts, so I'm gonna move on.
Just improve.
Stop that! Don't be disappointed in me, Niels. Stop that.
Oh, that's not enough for disappointment.
Okay.
I think I got something there.
Okay.
It's like SO3.
Mm-hmm.
I know why SO3 is SU2. Because when you take from the O, just the upper side away, then you got from the O and U. So you take one thing away. You take one thing from the 3, it's a 2.
So you need to like that.
Yes, you. So one thing away is like from 3 to 2.
Oh, sounds reasonable.
One thing,
Yeah,
you
it's
could
just
like maybe say what you actually want to do in the beginning.
Euler Angles.
What do you mean?
I mean, what is the purpose of your calculation?
So what's the point of the presentation? Maybe is your question?
Yeah.
Okay. So the people I'll be talking to have more knowledge on the subject.
Obviously.
And
I thought so.
No.
Why did you say it?
So they'll have more knowledge, and so what this is supposed to do is teach them a little bit about the subject. Because before I did this presentation, I looked at this and thought of O3, you know, maybe.
Also,
I had no idea what it was.
Yeah.
And so after a month and a half of researching, I learned what it is. And so the purpose of this is just to show other people about it, what it is mathematically and how it makes sense.
no, I mean,
So within a month,
what are you doing with these mathematics? What is the purpose of it?
Yeah, so physically maybe. So not for me, but like how science
You're not.
uses
I
it.
mean, you're not doing calculations to like do calculations, but to in the end get somewhere.
Just apply on something.
Yeah, you definitely do.
No, this is
This
just
a thing that I
math
would be finding interesting, like in the beginning of the talk.
No, but this is just mathematical theory, right? It's like Matrizenrechnung.
This is
For which
Yes.
class will this be?
Quantum and classical integrable methods.
Yeah, it's just math.
Yeah.
It's nothing about science, or
It's sciencely
Math is
inspired,
science, but yeah.
yeah, this is a math lesson.
math, yeah.
And then like notice how a couple
so
of
there's
times
not actually something you want to do with these.
there are,
But in another class.
but in another class, if I had longer, I only have 15 minutes, and I have to talk about their relation.
It's like one sentence to say what they could be applied to.
But I have. That's what this sentence was.
Maybe
Yeah.
W plus minus.
yeah,
is
but
boson.
Yeah,
what
but
is
both
something
are-
that's the last thing you wrote?
Weak
there?
force.
The last
So
thing.
you want me to encourage it with
In the beginning, like,
So,
we
so
will
my
use this
idea of
to
a talk is
read,
like
to
giving a
listen.
question.
No.
Wonder.
You need cute kitties.
cute kitties. So
Kittens.
could you come to my class? Simon?
Yeah.
Wonderful.
Yeah.
No, I mean, what like
So
inspires me to listen is when I in the beginning have a question and then this question gets solved step
Yeah.
by step. So this is my idea, but maybe it's not applicable or something.
it is. So the next thing is, I spend so much time learning how they make sense with each other. Like the universal covering is like the pride and joy of this whole talk. Like that's how they make sense together. That I didn't have enough time to figure out how it actually makes sense physically. So I've been reading books to figure it out, and this is the first 2 or 3 chapters, and where it actually comes in is like chapter 8. And I finally, the other night, found the chapter where it comes in, and I read that chapter, and it would take me at least 2 weeks to decipher what that one paragraph was trying to say. But that's something I can do tonight. I can go back and have Noah help me with understanding what that paragraph means, and then introduce that to them.
But this thing that you did down there was really cool. I mean, we could also just say in the beginning, like, we will talk about this, and I will explain you the connection. And this is interesting because later on we will see how they're connected too. So I will first start now explaining O3.
Okay.
And I wouldn't listen to what we're saying because you have no idea what this is.
Yes. It was just my
It was good. I loved your presentation.
Yeah, like you talk like
you guys don't because you just have no idea what this is, and I.
Yeah. So I think if the people who attend your class, they will understand because they got the knowledge they need to understand it. But are these like students like you are? Or?
Yeah.
Okay, so imagine you a few months ago, you said you didn't know what this means. So you should remember when you start that you had no clue what this is, and
if
this is their starting
point. If somebody said this to me 2 months ago, I would understand it.
Okay.
Yeah.
Yeah, well then it's fine. But yeah, you're expert in explaining that. So the way you present it is like quite professional. You really feel like you're made for being there and just explaining things to people who understand it. But the way you talk is so secure and everything. It's perfect.
It's awesome. Yeah.
And I did try to break things down, like what's
that was really cool. Yeah. Actually, can understand something.
Yeah, like if you would be talking about how to make pizza or so in the same way, it would be impressive.
It would be pretty awesome.
Like you start with powder and take some water,
to give a presentation.
and then a lot of cheese.
So if cheese is R is only the negatives. Cheese is not in it. Because negatives and cheese doesn't go together. I could be doing pizza.
Okay, so
I say scientific talk on pizza. No, I really liked it.
There's still Euler Angles, you guys.
Yeah,
You still have to
it's
hold
called
on for
Euler
a couple more
Angles.
minutes.
I hope there's more pizza in it.
This one's really cool because it's pretty.
Okay.
Yeah.
Let's go.
Okay. So
No, it was also good you drew like the graph and stuff because that really helps.
Awesome. Not me, but
okay, so
but you.
Are we starting from what we learned now, or is it a different topic
Wir haben
now?
auch gerade das mit dem,
different topic.
Oh, that's great.
wenn man das mit Tieren
Okay, then we can start again.
Okay.
Ja, ich habe auch Mathe für Physik.
Second chance now.
Okay, let's
So Euler Angles is how we rotate. And we want to be able to mathematically show any kind of rotation. And so how we do that is we have to make the parameters first. And I'll explain in just a second. Okay. Okay, so we would typically have, this is how we're going to start, an X, Y, Z. Okay. So what I'm going to do is I'm going to draw 3 rotations. I'm going to rotate this axis 3 times. And then with those 3 rotations, you can compose them such that any rotation you make can be made with these 3 rotations. So we're going to start with, so my head's going to be Z and X and Y, all right? So we're first going to start with Z is going to be the same, and I'm just going to rotate X and Y. Okay, so we're going to see that by X and Y are going to stay on this plane. X prime is going to come to about here. Y prime is going to go to about there. Do you understand?
You should have colors.
Yes.
Is it a flat space we're turning?
I'm not a fan of colors usually, but this would maybe help.
So I'm in a circle, I'm in a sphere right now. I just did that
Yes, it's
with
just
this
this
diagram.
part.
Yeah, just on this plane right here.
Okay.
Okay, now what I'm going to do is I'm going to make Y stay the same, and I'm going to rotate X and Z
It's gonna fly.
down, I believe. Yeah. So X and Z are going to come down. How that's going to look is now they're going to go on this plane. So Y actually z equals z prime. Okay, so now y is going to equal y prime, because this one's going to stand still. But now x prime and z prime are going to move down this. Okay, so then we're going to have some z prime here, z double prime actually. And then our x is going to come x double prime. Okay, so then I moved again. So what I've done so far is I've taken x, y, and z, x, y, okay, so x, y, and z, and then now I've just rotated again about this one. And now z is going to stay still, and I'm going to rotate x and y now. And again, it's going to go on a plane, and now I'm going to draw the other plane that it's going to go on. This one, I'm not an artist, so it's going to be a little bit more wonky. But it's going to be this plane. Okay, so now z is going to stay the same.
Yeah.
And that was a double prime. Don't lose that information. And this was a double prime.
Yeah, okay.
Okay, so now we just rotated.
It's gotta be triple prime.
Now it's going to go about z again. So then, now this y prime is going to come up here to y triple prime. And our x double prime is going to go shoop up to here. Okay. So with these three rotations, we can make any other rotation. And so why we need to do this? So something that I missed here was a way that they relate. So we don't know what the elements in here look like. So we have that. Remember the r's earlier? We know it's r something or other in here, and call it r in here. Well,
yeah, this would be an element. This R.
Yes.
Okay.
This r is the element. So it looks like a matrix. Okay, so, and we also said that O3 was a manifold of radius r, and it was a sphere. Now, about the identity for both of them, they're isomorphic, and what that means is they look exactly the same. They are a one-to-one onto function, so they're considered the same function. And how that manifests itself is they have the same Lie algebra. And what that means is that a Lie algebra is a really, really small infinitesimal rotation around the identity. So it's the identity plus some really epsilon small rotation, J, some rotation matrix around the identity. So now, if we do a lot of really small things a lot of times, if we do this n times, and then take the limit as n goes into infinity, then we get some finite rotation. And then this happens to also be the definition for the exponential theta. Because now you're not going some epsilon where you're going some actual theta. So what we just did, we went a really small amount away from the identity, and because both of these have the same identity, and because they're isomorphic at the identity, then when you exponentiate them, they're now the elements for these groups. Now where that comes into here is these are both rotation groups. And so how we make a rotation, so this element looks like e to the alpha, so something I didn't say that I should have is x to x prime. This was considered the alpha rotation, similar from y to y prime, is an alpha. When it went down, we considered this beta, and when it went over, we considered this gamma. Similarly for all of them. I guess guess tomorrow I'll actually have to do that.
Yeah, well, you probably have a bigger smart
So this is alpha J3 e to the beta J2 e to the gamma J3. Where J3 is a rotation around the z-axis. And remember we rotated about z and then y and then z again. And that shows in the J3 about J3, about J2, which is kind of y and J3. So any rotation that you make, because these are rotating objects in space, any rotation you make is made up of this. And if you want to do multiple rotations, if you want to do more than just one, do you guys remember the property for exponentials where if you have e to the alpha times e to the beta, you have e to the alpha plus beta?
Mm-hmm.
So here you would think, okay, so it's just this, and then you erase the e's, and then that works.
No.
Well, it doesn't here.
Are you allowed to do it since you have I2 and A3? So then the exponential laws are not allowed to.
Yeah, you're allowed. Because, see, this, okay, so like,
Also different.
call this general A and generally B. Then you could call this A,
Alright,
you
yeah.
could call that B.
Yeah, right.
But you can't do that in this case because the J's don't commute. And what that means, I'm still trying to understand. If you've ever heard of the uncertainty principle in physics, you can't measure the position if you measure the momentum.
Mm-hmm.
Okay, so that comes because the momentum and the position don't commute. So you can't measure them at the same time.
So yeah, one of them is always not sharp. You're like, if you focus on one, the other one will fail.
Yeah. And that comes from this right here, this quantum mechanical property.
Cool.
And so this
No, I know.
Huh?
Cool, no, I know.
And so because of this property, you can't just add these because addition, you can say A plus B and B plus A, right? So if we were trying to do that here, we would lose the fact that you can't just multiply this over here. You would lose that information. So you can't do this. So how you compose this is with the Campbell-Baker-Hausdorff theorem. Baker-Campbell-Hausdorff theorem. And so you do e to the h of j I j j, where h, j I, j j. Ooh, let's see if Kim you can remember this. J I j j plus 112 j I j I j j.
Just call it bubble.
It's an infinite sum of nested commutators. So see how this is j I j j? Well, down here we have j I commutated with a commutator, so j j. So when you want to do a lot of rotations, then you have to use this really complicated thing. And now let's see.
1 by 12.
I didn't know that was actually a thing until I came here. It's so interesting.
It is.
Why do you multiply?
No one claps when you give a talk in
So
biology.
is this where the Betragset gleich E' und so kommt from?
I didn't understand what you just said.
We had something in class. I didn't really understand that much. It was kind of similar to that. But
Ja,
Okay.
bevor sie nichts verstanden haben.
Ja.
Ich will jetzt auch noch einen Talk halten. Wir könnten uns jeden Abend hier treffen und dann ganz essen und einer erklärt irgendwas.
Ja, wollt ihr was wissen, was ich mache im Labor so?
Ja, ich habe auch noch, also ich habe eine halbe Stunde Präsentation aus dem Kopf, weil ich die gerade erstellt habe. Könnte ich jetzt
Könnte ich machen, wenn ihr wollt.
Ich.
Then I say,
Wäre so interessant, das betrifft nämlich Menschen.
Mein Talk wäre auch sehr interessant.
Der betrifft Pflanzen.
Aber auch Menschen.
What prime probability
Das ist ja auch
is the
Ich meine, das
derivative.
wären Pflanzenarten.
Das ist ja auch, wenn vielleicht rettet das uns das Überleben.
Nein, das kann ich mir nicht mehr bis jetzt merken.
Ja, aber das ist deine Beschränktheit.
Ja, das ist für mich so dumm.
it's really pretty. I took a picture of it.
Ja, hast du auch immer verdient.
Okay, so
Das ist cool, wenn es jemand so schlau ist. Das ist schon rot.
cool.
Someone's gonna send it.
Also das Bild ist voll schön geworden, jetzt was die
Ja,
gemacht
das
hat.
ist
Ne?
wirklich.
Do you know what an integral is?
Yeah.
Okay, I'm going to start with an integral then. So you have the integral from x to y
Was heißt das jetzt? Ne?
dx, where you have some function here, f of x dx. So you have some function. Call this x, call this y.
Das muss ich jetzt.
So now you know that how this integral is made, what this means, what's happening here is that you're taking an infinite sum, you're letting the limit go to infinity again, of these little dx's. So what's happening is you're taking, yeah, little sections here.
Where they're getting smaller and smaller.
Yeah, where the section's getting smaller and then you're adding up all the tiny sections. And what a derivative is it's a slope. Have you ever heard that? The derivative is slope.
Yeah.
Should
Okay.
leave the German word, but
Steigerung.
Yeah. Okay, so it's because, so say you take the derivative at this point right here. This is the line that comes from it. So then let's call this f of x, and let's let it be x squared. So then if you take the derivative of f of x with respect to x, then this is dx squared dx. And do you know what the derivative of x squared is?
Will look exactly the same.
What?
No, wait.
What? The derivative of
Derivative of x squared,
2 times x.
Or so.
2x. So how making derivatives works is if there's an exponent, you bring it down in front, and you subtract 1. Okay.
But it should be equal to the slope, right?
Yeah. And so what that means is that if you take any point x on here, then the slope is going to be a 2x. So the derivative
Yeah.
and this is taking the derivative. I feel like that wasn't a satisfactory answer because you haven't had your aha moment. I'm trying to think of a different way to explain the derivative.
no, because like I thought like these this equation Poisson complex numbers. So I thought it was like more like
More complex.
more complex. Okay.
Because when you're taking a derivative or an integral, you need a variable. You need to be working with a variable. And I is just the negative variance. And this is
Let's go.
just a number.
We're going to hear the next talk.
Wonderful!
Yeah.
I can also make one up, so we have at least 2 talks to go tonight.
Alright, so I'll finish up what I'm saying here then. So if you have an integral and it's got like I times x squared dx, then this is also equal to I times x squared dx. So if you have a complex number, it doesn't change your integral or your derivative for that matter. And maybe I'll look up a better way to explain it.
No.
Are there any more questions?
Ist jetzt auch konnotiert?
Nein.
Okay.
What? Why?
Ist das echt?
Ja klar.
Echt jetzt? Am Computer oder?
I want to hear you talk.
Yeah,
Okay.
I'd love to hear talk.
But the problem is,
I really need to.
I need a break
continue.
first. Let's go to the Mensa and then
Yeah, let's go to Mensa. I want to go.
we can go to the kitchen and
We can take
do
the
that.
whiteboard and hear the talk in the Mensa.
Yeah, that could work.
Wait. And see. Problem is, I only can show you the PDF without the animations because
I don't care.
That's
No
not-
animations. I don't think we'll understand.
without animations.
Nobody else laughed. I thought that was
Yeah, I can
Like
bring my
animations.
laptop.
Animations are stupid.
It's just simple.
I totally
Sometimes.
Fight.
Mostly when people use them,
Yeah.
they use them for like
It's like one. In short,
completely stupid stuff.
Yeah, it's like-
that doesn't need an
Okay.
animation.
you can do this. So you have a big X on the slide, and then you go to the next slide instead of just saying no, it doesn't work.
I
It's
mean,
like no, it doesn't
I
work.
mean, for
X.
something like your sphere and rotation thing, it would be awesome.
Yeah.
But for something like driving text onto the slide,
Okay, no,
it's
this is
just shit.
No, this of course.
Well,
Who
it always
does that in
depends.
uni? In uni, nobody is doing that. It's like appearing slowly or turning. I mean, just like
That's
animation.
the worst.
With animation, I mean just that you, for example,
Yeah, have like
Have-
this graph change or point
Yeah.
out something, like put an arrow onto a square, point out a special area.
or you make a special word in a text bold or something that you emphasize something or something. But no,
Or like you like when
like no movement or so. Just
when you explain a procedure, then you're
Appearing.
like the step you're explaining
Yeah.
is lightening up.
Every step you take,
Every move you make.
Okay, let's go to the kitchen then.
I'll be watching.
it's one minute.
Is it taking a break?
I'll be watching.
I didn't know that's what it sounded like.
Can't you see?
I'm glad that's probably on the video now.
No,
She
it's so
does.
great.
Hello.
Are we live?
Let's sleep.
I do not know.
No, it's still on.
Yes, we are still here. Hello, future people that will watch this.
Well, it makes
Future
it
people.
so
That's
interesting.
me tomorrow.
Normally I don't like videos, but now that I know it's future people,
It's future
it's so
people.
interesting.
Yeah.
Yeah.
Wow. This is me in the past. Look how stupid I was. Yes. Unbelievable.
Well,
Now you know.
I will head to the kitchen.
We should
to
get all
something
four
to
of
eat.
us really close so I can make a screenshot of it and it'll be like a picture. That was hard.
Oh, it's still on.
That's
I
Make a give out of
got
it.
it on video. I can't believe that.
Yeah, what do we do? Like, anti, like,
I mean, you're now taking this.
yeah,
You just
a
take
little
Yeah.
a screenshot later.
Yeah.
Okay.
playing ends, like they're social bonds. You know?
Wow, so we're taking 1,000 photos a minute now.
Yeah.
Okay.
This is actually going to be like a 2 gigabyte video or something.
No.
Yeah.
Really?
Yeah.
It's the camera.
High quality, I guess. You can zoom in onto the pimples on your face from way back there.
I have no pimples. Future me.
Oh, that was nice.